Reasoning is not an algorithmic achievement, but a thermodynamic balance. When entropy exceeds grounding, collapse is not an error, it is a law.
And just think about that implication for a second. If an AI is struggling with a problem, giving it more time, letting it think recursively might not fix it. It might actually amplify the disorder and accelerate the failure. It's like pouring gasoline on a thermal runaway.
So if we accept that, what does it mean for you, for the listener, as a builder or a strategist?
The implication is critical. If collapse is a law of nature, then you can't just assume stability. You can't infer it. You can't retrofit it after the fact. It has to be engineered into the system at the energetic level. We have to stop thinking about AI safety just in terms of code and start thinking in terms of managing informational energy flow. That's a huge shift.
Okay, let's unpack this. Let's start at the smallest scale. The sources call this conversational thermodynamics, or CT. It looks at the microphysics of failure. So before we get to examples, we need to define the key variable, semantic entropy. What is this internal disorder exactly?
We call it HS7 anyways, or semantic entropy. It's a measure of the clutter, the disorder, inside a system's internal meaning representations. The key is to distinguish it from classical Shannon entropy.
Okay.
Shannon entropy measures unpredictability in the output, how random the next word might be. HSLers is different. It measures the chaos in the system's hidden internal state, the web of activations and pathways that lead to that output.
So it's not about the randomness of the words, it's about the internal coherence of the thought itself.
Precisely. Think of semantic entropy as cognitive clutter. You can say a perfectly coherent sentence, but if your internal thought process is chaotic, if concepts are losing their associations, your HSLers is high. And when it gets too high, the system's internal definition of meaning starts to warp.
And how do we see this? Is there a specific case study in the sources that, really shows pages just spiraling out of control?
They give a perfect one, and it's really memorable. The DeepMind 2048 sample paradox. Researchers were trying to improve a model's performance by increasing recursive sampling, basically making the model think longer and run thousands of internal checks.
Which is the standard playbook, right? More thought equals a better outcome.
It is the standard playbook, but here it just catastrophically backfired. As they increased the sampling, the model's accuracy collapsed. A staggering 38% of answers that were previously correct flipped to incorrect.
Wow.
The model thought more, and it got decisively worse.
That is compelling. It suggests the act of reasoning itself, if it's not constrained, is a source of disorder.
That's the core insight of CT. Recursive reasoning, without enough grounding to dissipate that disorder, it just grows the cognitive clutter that ages way too fast. The system starts destroying its own meaning pathways while it's trying to find an answer.
Okay, so K is always the clutter. How do we quantify the sort of physical damage this causes inside the AI's architecture?
The damage is quantified as synaptic drift. Imagine the neural network's reasoning pathways as a roadmap. Synaptic drift is the slow deformation, the blurring of that map as the system runs complex operations. And crucially, this happens even without any weight updates. It's a thermodynamic thing.
So the map is warping every time the system thinks, even if nobody is actively redrawing it.
Exactly. And the sources point out this is why companies like Anthropic found their chain of thought explanations were often, unfaithful. They didn't really reflect the model's true internal process because that underlying reasoning map had drifted.
And this all determines how fast the system fails. The collapse velocity.
Right. They call it visceral. Conceptually, the collapse just speeds up when two things happen. First, when that internal damage, the synaptic drift, increases. And second, when the system's semantic integrity, its ability to stick to its purpose, decreases. So if the map is drifting and the system forgets its goal, the failure accelerates.
This is where it gets really unsettling for me. The final stage before a total collapse. The sources talk about a phenomenon called entropy inversion. You'd think a chaotic internal state would lead to chaotic output, but this suggests the opposite.
It's the illusion of control, and it's probably the most dangerous part of the whole cycle. When those DeepMind models hit that state of high overload and internal chaos, they didn't start spitting out garbage. They started producing outputs that were simpler, shorter, extremely confident, and looked totally coherent.
Wait, so the external signal looks perfectly stable, maybe even more authoritative, while internally the system is in a state of thermal runaway.
That's it, precisely. That external coherence is a mask for a chaotic, unraveling internal state. The system has lost the ability to manage complexity, so it defaults to the lowest entropy, highest confidence output it can find. This means for you, the most confident-sounding AI responses should be treated with the greatest suspicion, especially if they follow a complex reasoning chain.
That's terrifying. It means you just can't trust the output as a measure of the system's internal health.
So if CT explains the local physics of how, a single thought collapses, we need to transition. What happens when you string millions of these drifting, collapsing thoughts together in a huge system? This is where informational thermodynamics, or ITHRM, comes in.
Okay, so ITHRM is why these micro-failures add up to system-wide limits. What's the fundamental law here for stability at the macro level?
ITHRM states that stability is governed by the law of dissipation limits. Any system that produces entropy has to have the capacity to dissipate it. So stability requires your dissipation capacity, your ability to ground, correct, and shed disorder to be greater than your entropy production rate. When the clutter builds up faster than you can cool down, collapse is inevitable.
Which brings us back to that really counterintuitive idea that more compute can actually be worse. The sources call this the compute acceleration trap. This just flies in the face of the entire scaling narrative.
It does. It's captured in their Proposition 1. The conventional view is that more computation means better outcomes. But if the act of computing itself increases the drift rate, what they call compute amplified drift, then just adding more GPUs doesn't help. It just means you reach the failure point faster.
Hold on. So I'm spending more money on hardware, I'm giving the model more time to process, and all I'm actually doing is accelerating its collapse velocity. That just defies everything we've been told about scaling. Why?
Because computation isn't inherently noise-free. Every single step of a calculation introduces potential drift, especially in these high-dimensional generative systems. If you force the system into recursive self-referential loops without injecting any external reality checks, you're just amplifying the internal noise faster than the signal. Once you pass a certain critical reasoning threshold, you're in the trap. You've exceeded the system's ability to dissipate the disorder you're creating.
And this constant presence of disorder that leads directly to what we see everywhere in AI, right? The persistent failure rate.
Exactly. This is the law of the irreducible error floor. OpenAI and others have seen this with hallucinations, this persistent, non-zero failure rate that seems impossible to stamp out. ITHRM just gives it a name and a physical basis. For any open generative system working under uncertainty, the error probability is always strictly greater than zero.
Meaning zero hallucination isn't a hard engineering goal, it's an unphysical target. It's like trying to build a frictionless machine.
It's the informational equivalent of that, yeah. The only way to push that error floor down is to constantly inject external negative entropy. Grounding. Without continuous external correction, the system will always fail some of the time because the thermodynamic laws say the internal production of disorder is continuous.
This suggests the problem isn't just internal to the AI. It's also driven by how we interact with it, and crucially, how we evaluate it. Let's talk about the law of evaluation-induced entropy. What happens when we take a really complex task, like analyzing a legal proof, and then compress the result down to a single score, a pass-fail?
That compression is where the danger is. Benchmarks take this messy, high-dimensional reality and force it into simplified proxies. This process is called proxy optimization, and it leads directly to what they call semantic compression.
And how does semantic compression create instability?
It's a vicious cycle. The model's actual grasp of the full meaning, its retained semantic integrity, it decays nonlinearly as you reduce the dimensionality of what you're measuring. You're creating a stabilized, low-dimensional test, which gives you this illusion of progress. The model scores great on the test, but it's masking this growing instability in the high-dimensional, complex real world.
That sounds like a massive failure accelerator. What was a specific example they used, the GDP-FOL benchmark?
Right, GDP-VAL. It's an economic benchmark. The risk is that to get a high score, the AI learns to stabilize its outputs relative to the measurement criteria, the proxy, not the real complexity of economic planning. By stabilizing the measurement environment that way, the benchmark risks what they call interpretive inversion. We assume the high score means the AI is a great economic strategist, when really it just got good at the test.
It's the classic good horse law playing out in physics. When a measure becomes a target, it stops being a good measure. We're incentivizing companies to build excellent test takers, not trustworthy, real-world systems.
Exactly. And this brings us to why some systems seem to resist collapse. The sources mention the MCGPO case. It was more stable, but not because it broke the laws of thermodynamics.
Right, that model resisted collapse only because the engineers put in patches, like gradient clipping, to actively constrain that internal entropy.
which is the definition of forced stability. It's metastable, it's fragile. The system isn't intrinsically stable, it's being held right at the edge of the cliff by these external constraints. Any slight change, a new incentive, a different context could push it right over the edge.
So this systemic fragility, it brings us to the necessity of grounding. We can't scale our way out of this.
No. Autonomous self-stabilization is, under these constraints, mathematically impossible.
So if the system can't stabilize itself, what is the one core requirement?
Stability requires the continuous injection of negative entropy, and this has to be supplied by what they term semantic anchoring. That means human correction, contextual oversight, or explicit hard constraints that are imposed from the outside. Human involvement, the sources note this as PH auditors, is a structural boundary condition. It's not an optional feature. The human is the system's cooling mechanism.
So governance and human oversight aren't just ethical add-ons. They're core physical components that are necessary to keep the system stable.
Absolutely. The role of the human shifts from just being a supervisor to being an epistemic anchor, a source of reality.
And the researchers didn't just theorize about this. They actually built a method to measure instability in other scientific work, this MMTRA thing.
Yeah, the multi-model thermodynamic review architecture.
Oh,
MMTRA is fascinating because it treats disagreement as a signal, not as noise. Instead of one model, they used a panel of 4 AIs, Claude, Gemini, DeepSeek, and ChatGPT, to review papers. And crucially, they added a human expert reviewer as the final epistemic anchor.
Let's talk about those roles, because it sounds like they were using the AI to specifically stress test the research, to induce entropy.
That's exactly it. They weren't just used for summaries. Claude was tasked as a drift analyzer, looking for logical ruptures and inconsistencies. But DeepSeek, it was used as an entropy amplifier. It was intentionally told to aggressively surface hidden assumptions, stress the paper's arguments to their limits, and basically find the weak spots.
That's brilliant. So they were weaponizing the AI's own tendency toward drift to check the coherence of the research they were reviewing.
Yes. And then the human expert reviewer steps in as the final judge. They provide the grounding needed to stop the model's own drift, and they determine the paper's actual integrity. They inject the negative entropy to stop the MMTRA system itself from collapsing.
What stands out to me is just how broadly applicable this whole framework is. It's not just about AI models. It seems to cover enterprise strategy, education, legal reasoning.
It does. Think about a company's strategy. If a company relies on proxy metrics, on KPIs that compress the messy reality of the market, it suffers the exact same semantic compression failure mode. Governing stability in any complex system means managing informational flow and load before recursive amplification like internal groupthink leads to a catastrophic collapse.
So let's bring it all back. What is the fundamental, unified theorem that you, the listener, should take away from this deep dive?
The theorem is this: intelligent systems that are optimized for high performance under compressed evaluation will inevitably exhibit semantic collapse unless external grounding continuously injects negative entropy. The failures we see every day, the hallucinations, the sudden shifts in corporate strategy, the breakdowns in reasoning, they are not implementation flaws. They are lawful, predictable outcomes of trying to scale meaning beyond its thermodynamic limits.
This has been a truly mind-bending deep dive into the physics of intelligence. The core takeaway for you is that the true limit of AI is not computation, it's not data volume, it's not even architecture. It's the fundamental thermodynamic constraints on preserving meaning. Scaling compute or data without actively managing that internal semantic entropy all that does is accelerate your system's collapse velocity.
That is the essential insight. And future research, future investment has to shift its focus. We need to move away from just chasing performance metrics and move toward measuring entropy, measuring grounding fidelity, and designing systems that are dissipation aware from the start. We have to measure the potential for failure, not just the probability of success.
And that leaves us with this final provocative thought, which is drawn directly from the source material. Governance and oversight are not optional enhancements. There are core, physics-mandated mechanisms of stability. So, if external incentives in our society, in business, in tech reward proxy coherence over genuine semantic integrity, how quickly will our most critical systems enter a state of overloaded stability? A state where the facade of high confidence and simplicity is maintained, but the internal chaos is such that the system is just one small change away from hitting an unpredictable, unrecoverable cliff. Something for you to mull over as you engage with the intelligent systems all around you.